So I'm going to speak on kind of a potpourri of topics. So when I was approached to give the talk, it was sort of the main point was talk to something that the sort of an academic research group would be interested in, and where some fertile areas for research would be. So we're going to have a bit of a potpourri of topics. We've got some discussion. We'll try to minimize any discussion on CAN. I think there's only maybe one slide in there, and then we're going to talk about some of the key technologies and areas that are sort of current right now, kind of in the auto industry that are very relevant. And if there's time at the end, we'll talk a little bit about kind of what the regulatory side looks like. We may not get into too much of that. So let me get started. So at the start of every talk, we have to have the obligatory cars can get hacked slide with the list of kind of different events that have occurred over the years. And so we go back to 2010, where it was actually a sort of a true researcher within kind of the industry here, that they first kind of looked at the automotive threat landscape, and they did a lot of work on the various interfaces with it. The next one to highlight, ironically, is the target breach. And so the question is, why did I include that one here? That was included here because it may not seem like it, but that is really when the automotive industry, sort of the C-suite types, started to take automotive seriously. So 2010, we had fledgling teams looking at maybe cybersecurity for the product, but what really happened with the target breach was a CEO basically went down because of a cybersecurity incident, and that was really a land shift in the industry. And so at that point, at least within our company, suddenly my executives had to sort of communicate the cybersecurity for the product up to and including the board of directors. And so for the first time, they were sort of very interested in it, and it became kind of an area that they were explicitly focusing on. Then shortly thereafter, we had the Miller and VehicleSec kind of attacks. They were a bit more stunt hackers, but we have to include them in here. What was interesting about their particular sort of piece, it was what any pen testing sort of folks in the audience would say. A lot of it was low-hanging fruit, which is true, but I think the punchline was it was really 4 separate vulnerabilities that had to all be present for them to be able to do what they did. And so to be true, for them to be able to impact the vehicle, first, the Sprint network had to allow sort of peer-to-peer communication, which most cellular networks don't allow if you're in kind of an IoT space. Secondly, the IVI had to have an open port and service running. In this case, the IVI provider had a debug port that was sort of wide open and exposed to the network, and the firewall misconfigured so that that debugging interface was actually exposed out onto the cellular network. Then once they were in and had active access to the IVI, the code signing for the side of the IVI box that basically interfaced with the vehicle wasn't performed sort of properly. So what kind of all of those came together to allow sort of the first true remote exploit. The one in 2010, obviously, was similar findings, and they were able to do things with braking and whatnot. Since then, we've had other research, including one with airbag disposal. I'm not sure if folks are aware, but there is a required function within the vehicle that is for airbag disposal, and so there's a diagnostics interface that's sort of explicitly required under regulation that will deploy the airbag. And so that was an interesting bit of research in 2017. But we've come full circle then where we come into 2018, were VW and Audi in the same supplier, same sort of holes that were there in 2015 were still there in 2023. And I can't go into the specifics, but having worked with that supplier, we found similar holes even in modern stuff that they did. So that leads us, I think, kind of to an unfortunate punchline where there's maturity, but we kind of churn sort of through this. I'm making fun of sort of an SBD slide here a little bit. I know there's some SBD folks in the audience, and it's just a little bit of tongue in cheek. So there was a lot of industry hype early on that the SBD folks are kind of referring to here, and that calmed down as sort of the best practice and the legislative sort of pieces sort of kept up. And this era of maturity that was kind of described, I'm actually arguing, like a lot of other industries, it becomes a bit more of a sine wave. And I would argue that's the case in a lot of different ways. You've seen it with the cloud. You've seen it with anytime there's a major transformation sort of technology, it tends to basically, they don't think of the security of it initially, and then you basically have a dip, and then the industry kind of have to catch up again. And so it's this constant kind of sort of up and down motion rather than kind of this panacea of getting to the promised land, so to speak, of having proper security. So what in the auto industry is kind of driving that sort of state? And so a couple of things have driven the auto industry to even need to care about cybersecurity, but to also kind of be in that similar state where there's some improvement, and then there's some movement backwards. The first is obviously connectivity. Somebody had mentioned in a previous talk that embedded modems are becoming kind of the norm. I know most of the OEMs, it's fairly common, and it's nearing 100% of the fleet. Certainly in the major markets, you can still get some fleet vehicles or whatnot without modems or connectivity. But as you get things like Android Automotive and some of these other types of technologies, it's just going to be pervasive everywhere. And so connectivity is the first and biggest driver. Autonomy, there's been a lot of discussion here on autonomy. I'm not even talking the level 4 sort of autonomy that folks are sort of dealing with here. What we're really talking about is the level 2 plus, level 2 and level 3 autonomy, where it becomes a function of the vehicle being able to sort of assist with the driving. And so you've got GM, Ford, Tesla with their Super Cruise or Blue Cruise, or so there's Tesla's marketing it as fully autonomous. But what it really is it lets you essentially not worry about driving while you're on the highway, and essentially takes some of the driving away from you cognitively. But that autonomy still means that the vehicle's doing more and more of the sort of the driving. And that's actually in vehicles today, as opposed to some of the level 4 and level 5 pieces, which are a little bit further out in terms of time. The third piece is regulatory. We'll talk a little bit more about that later, but with UNECE passing R155 directive, for the automakers, this becomes sort of existential because it at least in Europe, it's tied with type approval. So in the US, we're a self-certification sort of market. So the automakers hold the liability, but we also declare that the vehicle is fit for sale. In type approval type markets like the European Union and some others, type approval or the regulators reviewing now cybersecurity, but historically safety, fuel economy, those sorts of things are a gateway to even be able to sort of sell into that market. And so if you don't pass type approval, then you basically might have an idle factory, and there's very big sort of financial implications to that. And then finally, is the business and technology piece. And so we're going to get into a lot more in this area, but like the hype right now is the software-defined vehicle. I know VW, Ford, GM, BMW, probably a number of the others have talked about the software-defined vehicle. We'll talk a little bit about what that means and why it isn't necessarily the panacea that it may pretend to be, at least initially. And then new use cases like the way that key fobs are changing and just vehicle access. And then finally, the charging system. Other thing to sort of highlight, product cybersecurity is different than your traditional sort of IT security. And this could cover kind of generically product security in many ways, but this is a bit unique to automotive in terms of kind of just the slide. But the focus historically in IT systems, it's always with the CIA triad, product cybersecurity, it's safety, safety, and safety, but then after that, sort of privacy, theft of IP, theft of the product itself, typically in your IT system. People aren't coming into your data centers and stealing a $70,000 piece of equipment, not usually, but theft is a big part of it. And certainly within Thatcham UK markets, the theft aspects of it become even more critical. It heavily affects insurability and a lot of other areas. Compliance, different set of compliance, and there's product liability, obviously, on the compliance side. The technological scope, this is interesting because, like, intentionally, so on the traditional IT side, it's the big expansion of late has been the cloud and APIs and IoT and a secure software development lifecycle. But you look over on the product side, very similar, having a secure connectivity, autonomy, but also API, cloud, and secure software development, as more and more of it's driven by software. And so just having a method to develop secure software isn't in itself sort of a necessary component of that. And I mentioned the cloud. We're not going to go into a lot of the detail, but if you look at identity and the monitoring aspect of it, historically, like monitoring in an IT environment, you're monitoring devices that you own and control, but here you're monitoring against devices that are owned, controlled, out of your hands. But even more interestingly, the users themselves may at times be the adversary. So you see things like odometer rollback, theft of services, hacking attempts, which all of you are obviously in the business of doing. And ironically, in the monitoring scheme, a lot of that, instead of being in the cool embedded space, it comes together at the cloud or the API or where the OEMs kind of have that connectivity point centered, because the real life attackers really find they're lazy and they want the most bang for their buck. In the wild, that's what you tend to find. And so cloud is easy to hack. They know how to do it. They got the tools. They've got the criminal networks. And that's what they basically will go after, because it tends to be the low-hanging fruit, and it's the point at which vehicles are aggregated. And so it's, at least for right now, it's not as interesting to hack an individual vehicle if you're going to attack that connectivity point where they come together. We'll talk a little bit more about the monitoring piece later. And then education. Every corporation tends to have kind of a education system to try to train users not to click on phishing emails and all of that. You're not going to do that with a product, obviously. You're going to basically, and in those cases, the users themselves could be part of the adversary system. And so we'll shift a little bit here to the technology focus. So there's already been a lot of discussion about CAN. So CAN is still going to be a thing, but what we're seeing, what's kind of in the midst of it is a transition to Ethernet, and that's kind of going across two evolutionary kind of steps that we'll get into in a second. With CAN, real-time trusted communication was the default, and unfortunately, within AutoSAR, as we'll see, it still is unfortunately kind of a lot of the mental model that pervades things. And so there's been a lot of research on CAN. It will still be present, but what you'll see slowly Ethernet will take over high-speed communications between sort of zonal modules, the parts that need to be connected to the internet, and then CAN will become a way to integrate legacy, real-time constrained modules. It'll become sort of like an I²C, a method by which you can connect to very small modules like door modules and legacy modules and things like that. CAN is still heavily desired, and a lot of people are like, why did we use CAN? It's very inexpensive. It's built into most microcontrollers. The RF capabilities of it are really well known and understood. It can be managed with 2 wires. Wiring is very, very expensive and adds weight and complexity. And a lot of the tooling is kind of integrated around CAN. So it still will be present, but what you're going to see is you'll see a shift where a lot more of the logic is done kind of over Ethernet. And when we say Ethernet, it's similar but different than what we're kind of all used to seeing in the IT realm. So we're building millions of the same sort of local area network, so to speak. So things that you would expect to see when you're building out like your home network or a LAN inside of a data center don't need to necessarily be there. And so things like DHCP or even ARP don't necessarily need to be present, because if you're building a million of the same network, why do you need different MAC addresses? Why wouldn't you just fix the IP address, especially where manufacturing, their mental model is, hey, as little variability as humanly possible so that there's as much consistency when the vehicle gets built and when it gets diagnosed. And so the mindset is you're building the identical thing over and over and over again, and you may be adding components, but they don't necessarily need that same level of configurability that sort of a true IT generated network would, or at least when it's exposed externally to the internet, potentially, but not within the internals of the network itself. Some very different use cases and a different mindset in terms of how Ethernet gets applied. And then finally, some very odd limitations, as we'll see, that kind of may get applied with AutoSAR. So what does it look like? And so this is a bit of a dumbed down diagram of what our current generation architecture, or one that's kind of in the interim, looks like. And so this, as the researchers or the Gartner type folks would say, is kind of the interim where you basically are using Ethernet to connect the higher speed pieces, but what you've got is basically Ethernet connecting the central gateway, core connected modules, and connecting out through the modem. And that way you can expand connectivity. The connectivity can basically flow cleanly between kind of these modules. How we did it in this instance, sort of in this interim instance, we created what we had as a central service-oriented architecture. How many here know what MQTT is? Have heard of that protocol? Probably half of the group. It's a protocol that was developed by IBM probably 20 years ago, I would think. Fairly simple in terms of its concept, but we used it basically as a central kind of hub. What was nice about it is it allows you to basically, it's a pub-sub model with a fairly simple network topology to it. And we basically allowed that to be the way that things were communicated over the network. We also required that anything that wanted to communicate in the network authenticated itself to that broker, or it's essentially the switch would block it down and not allow it to communicate anywhere else on the network. And so we could basically lock the network down, isolate the nodes from each other. And what's nice about the MQTT protocol, at least, is based on who's logging in, you can restrict what pieces, or they call it, the word they use is topics, or what topics they could be basically published to or subscribed to. And so that was how we initially kind of did the interim. So this just describes it a little bit more. So the permission model can be sort of done. We use MTLS, MQTT itself, historically used sort of a password-based mechanism but it allows you to kind of do it a number of different ways. So this is just an example of kind of like what the interim potentially looks like. In a second, we'll get into the sort of the adaptive AutoSAR piece. But this is an example of kind of the interim step. And so F&V X is kind of our nomenclature for it, a fully networked vehicle. This was essentially the second and third generation kind of description of that. And so this is an example of what's in production today. Take a little bit of a side tangent here before we get into the adaptive piece of it or the next generation. So diagnostics is kind of the other side of the coin that often does not get sort of discussed. I think the comment I would make to the researchers in the audience is a lot of focus on the first bullet there, normal mode messages, but I think most of the folks at the OEMs or within the auto industry would say, yeah, you're really dealing with the easy part. The soft, vulnerable underbelly of the vehicle tends to be the diagnostics piece, which is based on the UDS standard. And what does the UDS standard let you do? You can read and write sort of identifiers within the thing. You can read and write diagnostic codes, fairly simple stuff. You can execute a remote procedure call, and those are used for service or all kinds of other things. You can put these modules into a software download state. And when this was first developed, code signing wasn't a thing. So you could basically put the modules, back in the day, you could put the modules into a state where it would accept software based on nothing more than a CRC. Not necessarily the case now, but you could, and then you can request read and write memory, direct read and write memory access. And so folks that do things like build Forescan and some of these other tools that are out kind of in the wild have figured out this is where you can basically kind of poke the beast and get the maximum kind of bang for your buck, so to speak, in terms of enumerating through the UDS or unified diagnostic sort of pieces. So the standards up at the top describe how the basic protocols work and some of the required or regulatorily mandated UDS pieces. But there's a lot of it that's basically OEM specific in terms of like end of line routines and things like that. Why does that matter? The next piece here, so if you look at that date, 2020, so 2020 was the first time that ISO 14229 actually included some recommendations or mechanisms to secure diagnostics. And so you can just infer from that, you go back before that, most OEMs or a lot of OEMs, the methods were either initially there was no security definition, so the OEMs basically sort of define their own. And I can say a lot of the OEMs would often create it based on shared keys that would be shared across all the modules, just because of the way that the diagnostics works. Starting in 2020, ISO created a new standard that defined 3 different ways that you could securely sort of set up your diagnostics. And the way the diagnostics typically works is you put it into, so if it's in a default diagnostic state where it'll respond to certain diagnostic messages, then you request that it basically goes into a higher state like programming or extended diagnostics or end of line or something like that on a given module. And then there's a challenge response sort of scheme that's in place. And often that challenge response is not the strongest. But starting with this 2020 sort of scheme, there's a certificate-based method, or there's 2 certificate-based methods, one that's intended for use with a gateway to protect kind of everything behind it from a security perspective. There's one that allows for direct certificate-based usage or lighter weight certificate usage on sort of end modules that are real-time embedded. And then there's one that uses a derivative key symmetric method to sort of allow that diagnostics. What's really nice here is if you look at the repair ecosystem, from a right to repair standpoint, anything that's on that kind of tester that you give to sort of a dealer has to be made available to anybody that wants to be able to repair their vehicle. And that's kind of under the right to repair regulations or MOU that's with the state of Massachusetts and in place within the United States. And so that stuff will be published either directly or will be published through sort of the service manual or through the service tooling that can be made available to others. But with this new scheme, you can actually protect and limit the scope in terms of what that tester is able to do. Whereas before, you'd have to basically either put the keys directly in the tester, and we've seen OEMs, and there have been instances where we've had to do that, and that's easy peasy to reverse engineer out of the tester. As soon as you get the code, you just do a little bit of reverse engineering, and you're off and running. But finally, then the back end is in the place, and the tester will basically be issued either a certificate or a derivative key that allows it to communicate with the vehicle. That's the new standard that's coming in, and what you're going to see is that isn't necessary. Some OEMs will be faster to kind of migrate to this than others. I think everybody's in the stage of migrating to this. It's just a question of how fast and in which places. But the point I would make is diagnostics, super easy. You can reboot things. You can do all kinds of really fun things in cars, trucks, boats, everything. And it's, in many ways, much more interesting than the normal mode stuff. Jumping to the software-defined vehicle. So we talked a little bit about what the current kind of interim generation, at least for Ford, looks like. SPD's published something similar to this, where I think a lot of automakers are kind of in an intermediate place here. What they're claiming that the next iteration of this, and I took this slide from SPD to give them props, because what they described sounds really cool and the right way to do it. But as we'll see in a second, it isn't really how it works. And so what SPD is describing here is the desire is basically to consolidate ECUs into larger and larger groups that basically can have flexible sort of functionality, essentially applications, for lack of a better word, that can run independently of each other and basically control and manage vehicle sort of functionality. And what they're describing kind of in the words is, to do this right, we should really learn from IT and the cloud sort of groups where, hey, we should use container technology, isolation technology, sort of orchestration technology like Kubernetes and things like that. And that's kind of what they describe as kind of the end of this exercise. Unfortunately, what a lot of this, when they say software-defined vehicle, what it tends to mean is we're talking a little bit more about what's referred to as adaptive AutoSAR. And so there's classic AutoSAR, which has been around for probably a good decade or more. Classic AutoSAR tends to run on microcontrollers. Adaptive AutoSAR was the answer of running AutoSAR on essentially a POSIX-like operating system. And so what SPD describes, hey, we've got containers, we've got full sort of segregation, things can be separated out. What AutoSAR really means by it is, oh, that CAN-DB that everybody was talking about, what that really is, if you were to basically peel back the onion and kind of look within the automaker, it's a big XML document that basically they're modeling the way that the vehicle should work in terms of sort of a systems engineering perspective. And what they do is they basically say, let's just apply that to essentially a bunch of apps that are running. And instead of being CAN messages, these are API calls. And so, as we'll see in a second, so over Ethernet, those CAN messages become API calls. And it's still, everything in that model or in that universe flows from this mental model where most of the engineers, and this is where cyber folks, we get really frustrated, most of the engineers think in terms of that IDL modeling where they're basically creating these 100 megabyte or larger XML files to model the entire vehicle. And then they iterate through that. And of course, as security professionals, we will honor that model, of course. We will not step outside of the model. What I really mean by that is the model tends to model that happy path. And so the proper interaction between APIs, if I send messages out of order or I send messages that aren't expected, what happens? We've often found that modules will just lock up or behave like in the way that way you would not expect them to. Or if you don't just follow the model at all, because the model will say who should be talking with who. And if I just decide to ignore that, that becomes a problem. So what does it actually look like on Ethernet? Because as we say to our teams, from a security perspective, all of this abstraction doesn't mean anything. You have to look at the lowest common denominator. What's actually running on the ECU, what's flowing on the network. And so what we see when we peel back that onion is there are really two standards that Adaptive sort of brings into place. One is called SumIP, which is it's a wire level protocol to essentially do RPC calls over Ethernet. The bad news is it didn't include any security whatsoever in its design. Zero, none, zilch. The other option in the standard is you can use DDS, which has essentially like a MAC type security at the application level. And you can basically authenticate caller and receiver. The problem is most of the Adaptive partners have not implemented DDS. And so you're kind of, a lot of people are stuck with some IP, which is unfortunate. So then you say, okay, what's the next level down in the security stack? Well, TLS and IPsec in the standard may optionally be leveraged for security when you're essentially talking application to application. Except, remember the limitations we mentioned before on Ethernet, a number of classic AutoSAR implementations implemented TLS in such a way that, well, you only need one TLS connection ever, right? So you only can have one connection to one other peer on the network, period, dot end. That's how some of the classic implementations actually did it. And so then you quickly say, okay, well, I can't necessarily do that, or the overhead on these smaller modules is too much for TLS. Well, let's keep digging. Adaptive AutoSAR capable operating systems may optionally have enforcement on the actual identity of the local callers. And so when you're running these applications that want essentially an application here wants to talk to this module over here, in theory, there's an optional component there that say, well, should this app be allowed to talk to that other application? That is 100% optional. And so there's an IAM component that may optionally be used, again, through that modeling. It'll look at the model and it'll generate essentially a configuration file to enforce that. But it's not mandated, it's not required. And what we've seen is there's some Adaptive folks in the room that are working on Adaptive. They've provided it, but we've talked to others where they're like, oh, we haven't implemented that piece yet. And so it's all over the board in terms of kind of even being an option. Adaptive is working to solve some of these gaps via an API gateway proposal, essentially having a gateway that'll monitor these API flows at certain choke points in the network. And they want to model IP tables and ARXML as well, which I'm not quite sure what the point is. The point here is it's at the wrong layer. It's essentially trying to model stuff at a networking hub layer that needs to be modeled at the application layer, especially if a node is having multiple applications. It becomes too easy to basically sort of sidestep that stuff. And so even these sort of late efforts are going to be implementation buggy, and it'll be hard and aren't going to really solve it at the right layer. And so then MACsec, as somebody was alluding to, MACsec becomes kind of the fail-safe. And so what you're actually seeing is a lot of the switching vendors are scrambling to ensure that MACsec is natively supported within the hardware. And so you're going to probably see a lot of uptick in MACsec because a lot of the hardware, at least in this generation, is there. And a lot of the adaptive partners, as they've realized just how bad the security that they've implemented or that got defined in the standard is, that's becoming the fallback. But again, MACsec is great. Don't get me wrong. I mean, if you're just listening on the network, it protects it, but it protects node-to-node communication. It doesn't protect application-to-application communication. So you have an information sort of mismatch, which as security folks will just love to basically play with and pull apart and do bad things with it. And then the final piece is almost all of the security within this is considered to be optional or is left as an implementation, sort of an implementation sort of piece. And so what does it actually mean to build an app? And so when we say implement, the AutoSAR implementation was left as an act of the reader. So code sign. So when you generate these applications, code signing is mandatory. How you do it, completely optional. An app in the standard is nothing more than a process. And so it says it's a process. So it's separate. See, it's a process. It's separate. Nothing to do with containers, which typically means there's kernel level separation, there's chroot, jails, there's a number of different sort of kernel things. There's mandatory access controls. All of those, none of that is there. OS permissions and isolation is optional. So they suggest that you run an application as a separate user ID and GID, but even that, most are doing that, but anything beyond that is purely optional. And what's even more interesting is the library, essentially adaptive boils down to, if you want to just get to the nuts and bolts that folks in this room will understand, it is a POSIX process running as a unique UID that links to essentially an adaptive library. And there's nothing that says that it can't also link to CLIP and have access to everything that all the wonderful richness that the operating system sort of provides. And I think if everybody kind of recognized that, I think it would be fine. But what you get is this disconnect that we get over on the left-hand side, where the business hears, hey, we're going to do, just like if you're using like Google Automotive, we've got an app, we can do an app store. Well, no, what you're really saying is, I can do it, I can manage that IDL easier. Well, that's not sexy to the business sort of side of the equation. Normally, when we look at this, APIs get bundled into an SDK. And the SDK gets managed and essentially managed in terms of compatibility. Adaptive and the AutoSAR model doesn't manage SDKs, it manages versions of that massive 100 megabyte IDL. It doesn't even, I mean, if it was a little bit more coherently created, you'd slice it up into sort of SDKs that could be managed on an app or an ECU level, but that's not how it's done. Apps can be built separate from the image. The mental model is weeks or months, not years. Whereas in the app world, anybody can build an app at any time, anywhere, any place, and deploy it. And so that's what we're seeing. And so then the last point, as we said, it's a process that's running on its own. Whereas if you think apps and App Store, if you look at Android or Apple, they have a runtime. It's been hacked at times, but that's the intent. Is it's a very carefully controlled app runtime with very explicitly granted permissions, either by the user or by the device. And that is not what you're getting with adaptive. And so to wrap up adaptive a little bit, we may someday in some future iteration get to the point, or that panacea that we started with SBD, where we can run apps safely, securely, and in an isolated way, but it is not the case today. And so a lot of the hubbub on software-defined vehicle is really kind of built on these predicates. And I think a lot of, from researchers, I think are going to have a fair bit of work on their hands to kind of look at and shake this out, or kind of prove that there's some gaps here. And it's going to take a number of iterations. And unfortunately, automakers are going to have to kind of live through pain, because a lot of this has been sold as the next greatest thing. And it's not just one automaker, but it's a lot of them, unfortunately. Transitioning a little bit, let's check my time here a second. Talking about the sort of areas that are right for research. So the electrification ecosystem, I think, is the other big one, that there's a lot of easy things that can be managed, or that researchers can look at. So I'll just give our experience. Why would an automaker need to be involved in the sort of the EVSE domain? Not that we're in the business of deploying sort of electric vehicle chargers, but when you buy an electric vehicle, as you would expect, you have to get an electric vehicle charger that kind of comes with the vehicle. There might be instances where we have to deploy them either to the dealerships or to other sort of ecosystem, just as part of the nature of the electric vehicle sort of ecosystem that's there. From a regulatory standpoint, I'll touch on that one briefly. From a regulatory standpoint, automakers are heavily regulated in the U.S. at least, by the Department of Transportation and NHTSA, and they have been very clear. Cybersecurity is part of that domain. This domain, in theory, would fall under Department of Energy, but they've punted it, saying, "Oh, we don't have the regulatory kind of oversight. Maybe the states should look at it." And that becomes a challenge, as we'll see. So in this instance, kind of say, what can you see here? I can't, with the lights, I can't ask the crowd, but the context here is this is a large footprint commercial DC fast charger, supporting full 1511.8 plug-in charging, and retails for about $50,000. And so from a security standpoint, what state is that in? So this is the high-end charger that you would potentially see at a supercharging place. Well, they used a Raspberry Pi plug-in on their main board to control everything. And you can see, just kind of skim all of the security gaps when our team went through. And we see this time and time again in this space. The response from this, we won't call out, we won't name and shame the manufacturer here, but the response was, why do you care? This is in the field already. Nobody else has complained about this. And so that's what we're kind of living with. And so it's really sort of a gap. Second sort of example here, why this is kind of fertile soil. This is an example of more of a home charger that you would sell into, sort of install into your home. It hooks up to Wi-Fi, so it would be on your local network. This particular provider had fixed Wi-Fi SSID, access credentials, login credentials, and then once you were in, you could basically change the endpoint of the OCPP server. So if you guys are interested in electric vehicle stuff, we can talk, but OCPP is a standard in terms of how to communicate charging status to a sort of a back-end system. The standard itself, with 2.0, it's finally becoming slightly secure. But in this case, you could change that responder. And in this case, the provider basically used that responder to do OTA updates. And then they didn't bother to do code signing. So essentially, once you had access, drive-by access, you could basically reflash the firmware in this. And my team found that, and they weren't happy that they had to go and fix it. But that's just a sort of an example of what we as automakers are kind of seeing in the ecosystem. And It'd be great if there could be some regulation. I mean, the Europeans are starting to look at that, and unfortunately, I think the U.S. is getting a little bit behind. We as at least Ford have said to the U.S. government, you should really, with some of this great infrastructure money that's coming along, you should really to get that you should predicate it on some of the cybersecurity best practices that NIST and DOE have put out, but haven't felt that they can basically mandate. So we're going to skip the digital keys because we're near time. I want to leave a little bit of time for Q&A. So monitoring the ecosystem, I'm not going to spend a ton of time here, actually. The main point is every automaker is kind of having to figure out what the monitoring sort of piece of it is. It's required under the UNECE requirement. And so it's not like monitoring your traditional IT ecosystem. It's a lot more sort of monitoring, gathering a lot of the data from the vehicle, and gathering, I would argue, you have to gather a lot of the data from your the whole ecosystem. So not just the vehicle, which some OEMs have kind of had that view, but it's also got to be from the cloud and the identity management platform. And that identity management often is the soft underbelly, unfortunately. But that holistic view is what you really have to have situational awareness. And it becomes harder because in a traditional IT space, you go, oh, something went wrong, we'll go fire that individual, or we'll isolate their device on the network. Here, you have to think very cleverly in terms of when you find something, so what? What do you do about it? And we've seen a lot, and that's the thing I would challenge everybody that's doing research. When you come up with these IDSs, a lot of times as an automaker, I look at it and I go, so what? I don't care. If you find something, it has to be actionable or it's not of any value, really. And I'm saying that as a technologist, but our lawyers will say the exact same thing. And so that becomes kind of the bottom line. I think we're about at time, and so we're not going to spend a lot of time on the regulatory piece. So I will jump to the first slide and then say, are there any questions in the last kind of 8 minutes that we've got?
Okay, yeah, thank the speaker. See a question there. So you want to come to you maybe here. Please first and then you will go next.
Thank you for this presentation. As a cybersecurity researcher, I work on automotive Ethernet security by building intrusion detection systems based on deep learning. As you mentioned, on the Vehicular Security Operations Center, we can leverage some machine learning solutions to build intrusion detection systems for detecting attacks. Our main problem regarding the Ethernet-based communication is that we don't have a data set that is available that models the attacks, that shows us the attacks that are on the different in-vehicle network protocols, such as the UIP and other protocols. But today, as you mentioned, two main topics, which are the in-vehicle network security and also the software-defined vehicle. I was wondering if you found out some vulnerabilities on the SOM-IP protocol, which stands for the Service-Oriented Middleware Protocol, because it works both on the software-defined vehicles, where we need to find a SOA architecture that's able to handle the different applications on different operating systems, and to also, is there any data set available? Can Ford publish these data sets, or what exactly? And thank you.
I think that the challenge you got is the researchers in some ways, unless they can partner with some of the tools makers that make like the adaptive implementation, and I know there's one here, it becomes a little bit tricky because, like in the case of like the SOM-IP or the way the modeling works, automakers tend to be very protective of that first, and secondly, a lot of that's being built now as we heavily sort of in flux in future products. I know, I read in the trade that like VW, Ford, BMW, leaving out a bunch, are in the process of kind of that transition. I assume most of the other automakers are, but it's in a state of active development. So that becomes hard to say, oh yeah, we'll give an active data set for a product that doesn't doesn't exist and isn't in the market at that point.
Yeah, just one special request, because I have already published a paper regarding some IP intrusion detection using deep learning, but the main problem is that we don't have sophisticated and stealthy attacks on the some IP protocol. So if once deployed, I hope that we can find several attack types which are really stealthy to be detected.
Yeah, I think the biggest thing, if I were going to attack some IP, what you would probably try to do is get execution level access at one of these nodes that has the applications, and then basically violate the identity access management sort of piece, and see if you can get some IP messages out directly into the network, making calls that it shouldn't be making. And that's likely what it's going to look like, but how to track that is going to be sort of an open question.
Yeah, especially on the service discovery feature, I think.
Yes, exactly. And it's not like it's a little better than CAN. It's got a sender and a receiver, but it's not that much better than CAN. I'll just leave it at that.
Thank you so much.
Yeah.
Hello. I work on campus security mainly. At the beginning of your presentation, you were mentioning multiple things on the adoption of the vehicle industry, them adopting Ethernet and then that replacing CAN little by little until CAN becomes something like I2C. So my first question is, when we say CAN, are we here talking about standard CAN alone, or are we also including certain things such as CAN FD, CAN XL, and those things? Also, when we talk about automotive Ethernet, that also is a little bit vague. So automotive Ethernet has multiple standards. So there's the switched version, right? And there's also the newer versions such as T1S and stuff like that, which look a lot like CAN. It's a bus. Eventually, it's Ethernet, but it's
yeah, they always want to make it look like CAN, unfortunately, but yeah.
No, but like I know that wiring is a big problem for the automotive industry. So like them adopting something like switched Ethernet all over the vehicle, that would take that would require a lot of wiring. So I wanted to know your views on that.
What you will probably see is there's going to be a couple of tiers of Ethernet. So CAN, for those that don't know, is essentially a two-wire twisted pair sort of technology. Does really well against sort of RFID, or that RF interference. The first deployments of Ethernet that I have seen typically will be like a four-wire. Essentially, they'll take, it's not exactly this, but essentially four wires are essentially kind of two CAN lines, and you can get several hundred megabytes of bandwidth through it. There's still, I think, an open debate among automakers and the industry where the faster sort of speeds like 1 gigabit or even up to 10 gigabit speeds will be sort of necessary. Can't get into a lot of the sort of autonomous vehicle architecture piece, but there are certainly use cases in that domain. But then gigabit and 10 gigabit Ethernet, it will probably kind of follow that same path where it's on a certain handful of links that need that higher bandwidth, and then the quote unquote slower Ethernet will be to the IO aggregators that are aggregating up like powertrain and body control and things like that.
Okay. Thank you.
I'm not ashamed to demonstrate my ignorance, so I'm curious how broadly you define your scope. In particular, I was thinking of the Hyundai/Kia remote door openers giving access to the whole car and plugging into a USB cable and stuff like that. And as one example, and then as another example, the VW lying about emissions, the software that lied about emissions. I wonder whether you include both of those, which are two very different things, in the scope of what you cover in trying to secure the automotive infrastructure.
They would both be in scope, but in slightly different ways. And I'm like thinking how to not kind of, because I don't want to necessarily kind of go.
I'm not asking you to bash your computer.
Yeah, I go after other automakers. So the Hyundai, the Kia one with the USB. For those that haven't seen it, you can Google it. There's a number of YouTube videos. That was more. My understanding is from what we can discern. With the same public information that everybody else has, they did not include an immobilizer, which is sort of the most recent version of like how PFOPs typically will work, and they thrifted out some of the traditional physical security on the steering wheel block to allow it to easily be moved, and it just happened to be the shape of a USB stick. There's not any data there. Even if the screwdriver, it just kind of force it into an ignition on position. So that was more as much a physical security issue, and I don't know what politics were going on within the company, why they kind of removed some of those pieces that are fairly common in the auto industry. And then for the VW Dieselgate, I think that was as much a corporate compliance sort of issue as much as anything, where they weren't reporting, or they were basically, they were shooting out the software so that it could detect if it was in an emissions state or where the emissions was being measured, and then change the calibration so that it would meet emissions, and then when it was actually on the road, it would pollute more and be wouldn't be as clean.
Right, but what I'm wondering is, are you focused on the behavior of the software in a formal verification sense or something like that, which might have detected the VW case because it had to be formally specified, if this happens, cheap?
I'm going to give a bit of a cheeky answer. In the VW instance, it was the company itself that did it. So if they were doing formal verification, I don't know that it would have helped. Formal verification, and kind of as a concept, is interesting. It tends to be really heavy on the amount of analysis that's needed. So it's now, I don't believe it's that heavily used in automotive. Maybe in a handful of very specific cases, but it's not sort of used widely across the board. Yeah.
Okay, so I guess we are at time. So I guess for more questions, feel free to find Mike maybe after the talk, and let's thank the speaker again.